We've now introduced lists, ordered sequences of elements. Elements can be almost anything, and they're mutable. And we've seen examples of how we'd like to use them. We can slice, we can clone, we can index, we can have arbitrary structures inside of them. We're going to take a slight detour just for a second to talk about functions, but we're going to bring it back to lists in an important way. First, I want to talk about the idea of a first-class object. And we'd say a data structure, a data type, is a first-class object if it has the following characteristics. It has a type. It can be an element in a data structure, like a list. It can appear in an expression, like an assignment statement. It can be on the right-hand side of the assignment statement. And it can be an argument to a function. Now, it's pretty clear that ints, floats, strings all have those properties. It's easy to believe that lists and tuples would also have those properties, but so do functions. Now, that's interesting, right? Does a function have a type? Well, that's easy to believe. Could a function be in a data structure like a list? Well, if you think about how we create lists, we're simply getting values of expressions and creating a structure where elements of the memory point to those pieces. So if I gave as an element of a list the name of a function, thinking back to our environment model, it's easy to see how that element of the list, that spot in the list, could point off to that data, that particular procedure object. Okay. Can they appear in expressions like the right-hand side of an assignment? Sure. I can say x is going to equal factorial of 5. That makes sense. And then can they be functions? Can functions themselves be arguments to other functions? That's interesting. And we're going to see that that can actually be the case. And this idea of having a first-class object for a function, or having them be first-class objects, is particularly useful when we're going to use this in conjunction with lists. And we often refer to this style of thinking or programming as higher order programming, where we are treating functions as if they're elements of data structures and applying functions to them. Let's see if we can make a little bit more sense out of this by looking at an example. I'm going to write a little procedure here called apply to each. It takes two arguments, a list, L, and a variable whose name I'm going to, a parameter whose name I'm going to call F. And I'm going to assume that L is a list and that F is a function. And what I want apply to each to do is to walk through the list, mutating each element in turn by replacing it by what happens when we call the function F on that element. Okay? So the code doesn't look too bad. I've got a little loop where I is walking from 0 up to the length of the list, or 1 less than the length of the list. It's going to get all of the elements of the list. And what am I doing? I'm going to get the ith element of the list. I'm going to call F on it. And then I'm going to change that ith element of the list to be that value. Let's think for a second. If we think back to our environment model, if I applied this where I passed in for F some function, square, we said that we would bind a local frame where the variable F would point to the value of that parameter, which in this case would be square. And then when we executed the body of apply to each, we would simply be using the value of F, looking it up. So in essence, we would simply be substituting in for F. I'm not going to do the example of the environment model, but what we just described makes sense. So let's see if that actually works then. Let's take an example of this. So I'm going to walk through this in sequence. I'm going to do apply to each, and I'm going to start with a list L that's a set of numbers, 1, -2, and 3.4. And I'm first going to call apply to each on that list L with the built-in procedure abs called on it. Okay? What happens if I do that? Well, I know, if I think again about my environment model, I'm going to create a frame. Apply to each is some procedure. I'm applying it, so I'm going to create a frame in which L will be bound to this structure, and F will be bound to what that points to, which is a procedure object. And then, what am I going to do? I'm just going to walk down the list L, at each point applying F, which is bound to abs, to each element of L, and changing the value. And if I do that, what I get is that when I print out L, it now has that form. I've mutated L. And yeah, the 3.4, because of the way we represent floating point numbers, doesn't quite come out the way you'd like it to, but we've changed L. And what's important to see is I've run through a loop where I'm just applying a particular value of F, in this case bound to abs, to each element of the list. Now, having changed L, let's do it again. Let's apply to each. Again, the list L, now at this form of 1, 2, and 3.4. And in this case, I'm going to use int. And again, what it says is up here, I'm in essence binding F to int in a local frame so that when I'm evaluating this body, F points to the internal procedure int. And if I do that, I now get a new version of L. Actually, that's a poor way of saying it. L is still there. I have mutated L so that it now has the values 1, 2, and 3. What about fact? Let's assume we got fact. Factorial is available to us. We can do the same thing. And it now gives us the first, second, and third values of factorial, or fact of 1, fact of 2, and fact of 3. And now that I've changed L again, let's do one more time. Let's do it with fib to get the first, second, and sixth Fibonacci number. And out they come. What I want you to see here is that we can pass in a function as an argument. We just did a different function each time. In terms of how things work in that environment model, we're just locally binding in a frame the variable f, that parameter f, to some value function. And then in the body here, we're simply looking up the value of f and using it. And by the way, if f had just been a name for a specific procedure, we would have done the same thing. If we'd said int instead of f, what would we have done? We have looked up the binding for int up in the global environment, which points to a procedure object. So here we're just passing them in as we go along. That's actually quite nice, all right? That says we can do a bunch of interesting things with functions. But we could do it in a different way. So for example, I said that functions could be elements of lists. So let's think about one where instead of applying a function to a list of numbers, let's apply a list of functions to a number. So here's apply funds. It assumes that L is a list of functions. It assumes X is a number. And what's it going to do? It's going to loop through each of the elements of the list and call that function on the number and then print it out. And so if I actually run this, well, let's do it over here. Let's go check it out. I've got a version of it over here. And let me just load this up into my idle environment. And let's call apply funds. And we're going to give it with abs, int, fact, fib, which I've defined in my file here. And we'll give it the number 4. Very cool. That's really neat. What did it do? It ran through a loop where it first started off with abs as the binding for f, and then applied abs to 4, printed it out. And then in the next loop, it got int and applied int to 4, which is pretty boring, printed it out. And then it took fact and applied fact to 4, printed it out. And then fib and applied fib to 4 and printed it out. What we can say is that those functions can also be members of lists, and we can loop over those using them in places where we would like them as well. Very nice. Let's take this one more step. We can generalize these higher order functions a little bit more. And in fact, Python provides some general purpose higher order procedures for us. One of the ones it provides for us is the procedure map. And what does map do? In its simplest form, it takes a unary function, that is a function of one argument, and a collection of suitable arguments. If it's a function of numbers, it better be numbers. And basically, map literally maps this function in turn down each element of that list, giving us back the result of applying each of those elements to that list. So it's a little bit like apply to each, but it's basically capturing the same thing. However, map is even more general. We can give it an n-ary function, that is a function that takes n arguments and n collections of arguments. And map will apply this function in turn to the respective elements of those arguments. So in the case of min, where min takes 2 arguments, I can give 2 lists, L1 and L2, to map, and it respectively applies min to that pair, then min to that pair, then min to that pair, to create this list that it returns. We're going to come back to this idea of using functions in this way, using higher order procedures throughout the term. But you've now got a sense of, once I have lists and once I treat functions as first class objects, the kinds of things I can start to do with it.